Welcome to the second lecture on the topic of optics and lasers. Today we are going to discuss about Fraunhofer diffraction in depth. We will see how Fraunhofer diffraction occurs at a single slit. That's the first concept which we are going to consider. Whenever there is a single slit or a single obstacle, the gap is a single gap. How does Fraunhofer diffraction take place? So let's consider monochromatic incident light so that we get plane waves being incident on the slit. So this is a slit A to B. This is the slit. O is the center of the slit. You have a screen here and P is the central point on the screen. Now what is going to happen is when the plane wave front from the monochromatic wave source reaches the slit, each point on the slit is going to act as a source of secondary wavelengths. So if all points are in phase, then we will have coherent emission, or that will result into interference. Remember, only coherent sources will result into interference. Now waves which travel in parallel to OP, distance that is from the center of the slit to the center of the screen, waves which travel in parallel to OP will get focused at this point P. There is a central point on the screen. Now waves which are at points equidistant from this point O will also travel the same distance to reach the point P. So all these are parallel to the central ray or the central wave. So you can say that the path difference between the waves is 0, and this will result into a maximum intensity at the central point P. You get the central maxima. Now we are going to consider a point Q here on the screen. At present we don't know whether it is a bright fringe or a dark fringe, whether it is due to constructive interference or destructive interference. So in order to understand that, what we are going to do is we are going to divide the slit AB into 2. So if the slit's distance AB was small d, now it becomes half. So that means it is d by 2 is the distance between top of the slit to the center, and once again from the center to the bottom of the slit. So AO is d by 2 and OB is also d by 2. So what happens is, if I consider interference happening from this point A, waves originating from the secondary wavelets at point A and from point O, then the path difference will be lambda by 2. Path difference ON is going to be lambda by 2. So the way we estimate path difference, everything remains similar to the how we understood Young's double slit experiment, how we graphically understand, and the path difference remains exactly similar to the Young's double slit experiment which we have seen in the first lecture. So the path difference ON I can find, so this being the angle theta, angle of diffraction theta, I can get sin theta is ON divided by AO, that is ON is the path difference, I will get it as d by 2 sin theta. That's what we are having here. O by N is equal to, ON is equal to path difference ON is equal to d by 2 sin theta. Now the path difference, since we have divided the slit into 2, the path difference is now lambda by 2. So because of that, our expression becomes lambda by 2 is equal to d by 2 sin theta. So lambda by 2, path difference being lambda by 2, will actually result into a destructive interference. So that means we are going to get a dark fringe at this point Q. So whichever ways will have a path difference of lambda by 2 will cause destructive interference, and they all will be separated by a distance of d by 2. So d by 2 is the separation. Say from A to O, be it from A to O or O to B, I am going to get dark fringes. So from A and O, it's actually going to result a point Q over here, and from O and B, it is going to result into a point, say I'll call it as Q prime on the other side. So that's the first minimal point. So at the center we have the maxima, and next you have minima, that is at point Q, and another point Q prime on the other side. So we have the expression now for the condition for destructive interference as d by 2 sin theta is equal to lambda by 2. So I can rewrite this as sin theta is equal to lambda divided by d. So further, if I divide this slit instead of 2, if I divide it into 4, 6, 8 like that, it's always going to result into destructive interference. So this point Q you got when we divided the slit into 2. So to get the second minimal point, we should divide the slit into 4. To get the third minimal point, we should divide the slit into 6, like that. So every time the condition is going to be sin theta is equal to lambda by d. So for varying order of fringes, I can write sin theta n, I can generalize this as sin theta n is equal to n lambda by d. That is the condition for destructive interference in the case of Fraunhofer diffraction at a single slit. Sin theta n is equal to n lambda by d, where n is equal to 1, 2, 3. That is the order of the diffraction in order of the fringes. So in a similar way, I am going to consider for brightness or constructive interference. So for constructive interference, say I consider a point R over here. So how does it form? So for this particular point R, I am dividing the slit into three parts. That is, so each of them, so when the total distance AB was small d, now when I divide into 3, I will get it as d by 3 as a points, separation between the points. So d by 3 is the separation between the points. So if I consider this first point and the next point over here, actually they will be having a path difference of lambda by 2. That will actually result in a destructive interference. But the third point at the bottom will have a path difference of lambda. So when I divide into 3, when I divide the slit into 3, the first 2 points will interfere destructively with a path difference of lambda by 2. But third point comes into picture, which is having a path difference of lambda. So that means it is going to result into a constructive interference. So we will get a bright fringe over here, or a bright spot, or the maximal amplitude here. So I can write that if the path difference is odd multiple of lambda by 2, then exactly like how we got an expression in the case of destructive interference, for constructive interference, I will write d sin theta n is equal to 2n plus 1 lambda by 2, or sin theta n is 2n plus 1 lambda divided by 2 into small d, where n is equal to 1, 2, 3. So remember, for bright fringes, we need to divide the slits into odd numbers. So it will be 3, 5, 7, like that. So when I divided into 3, I got the bright fringe. That is the first bright fringe after the central maxima. So central maxima, we had obviously maximum brightness, then we get the dark fringe, and then we get the next brightness, then like that it goes on. So if I consider the distribution of intensity, this is our central maxima. This is the next point is here, that is actually a destructive interference. Then you have the maximum brightness. This brightness is what you have got. This is the next brightness which you have got, next constructive interference which you have got by dividing the slit into 3. Then again a destructive interference happens when we divide the slit into 4. When I divide the slit into 5, I get a brightness. So it goes on towards the other side also. So central maximum, we consider the whole slit. So all the rays, all the waves which were parallel, they all resulted into a central maxima. Then we divided the slit into 2. You get destructive interference. We divide the slit into 3. You get constructive interference. Then you divide the slit into 4, once again destructive interference. Divide the slit into 5, once again constructive interference. So again it has resulted into alternate constructive and destructive interference, or alternate bright and dark fringes. Now let's consider this condition that if the second lens, which is having a focal length f, so this is the second lens which we have, if this is close to the slit, or suppose if the screen is far away from the lens, that means this second lens, in this case of Fraunhofer diffraction, we are going to consider either it is close to this slit or else we keep the screen very far away from the second lens. So if the focal length of the lens is given by small f, then and if the distance between, say, the central maxima and the first fringe, which is the dark fringe, is x. So focal length is f, focal length of the lens is f, and distance between point P and Q is x, then I can get sine theta as x by f. Sin theta is x by f. But we already know sin theta is lambda by d. We have already seen it here. So for the first destructive interference or the first minima, we get sin theta is lambda by d. So if I substitute it over here, it becomes lambda by d is equal to x divided by f, or x is equal to f lambda divided by d. Now why did we do this? So x was the distance from the central maxima to the first dark fringe. The same distance x is applicable, say, from this central maxima P, say, to the first destructive interference towards this side. Both the sides, it's from the central, it is central maxima, it is, the distance is x. So if I come over to this representation of intensity, so you can see this is our first dark fringe, say, on the left hand side, and then you have the first dark fringe on the right hand side. So this was our central point. So the distance from this central point to the first dark fringe is x, the same on the right hand side. So the total distance is actually 2x. So from this figure we can see that this total distance is nothing but the width of this central maxima, is equivalent to the width of the central maxima. So I can write width of the central maxima W is equal to 2x. So I multiply x by 2, it becomes 2 into f lambda divided by small d. So f was the focal length of the lens, lambda wavelength of incident light, and d is the slit width. So very important point to be noticed that the width of the central maxima W is proportional to the wavelength of the light and inversely proportional to the slit separation. So let's see what is going to happen. If W is proportional to lambda, that means waves which have higher wavelength will always have maximum width. The width of the central maximum will be more. So that means the width of the central maximum for an incident red light will be more than the width which we get for an incident violet light. Because we already know that the wavelength of red is higher than that for violet. Now we have this inverse relation between the width of the central maximum and the slit separation D. So that means if slit separation decreases, the width of the central maxima increases. So we are exactly going to see the same here in the figure. So this was when the separation D was a particular factor. I reduce it further, so the width of the central maxima, that is the distance between the first two dark fringes on the left and the right, that is now increased. Again decrease the slit width, the width of the central maxima increases. So that means if you need more intense central maxima, then the slit width should be higher. We also see that the intensity and the width of the central maxima drops down if the slit width decreases. So let's consider a case if we had incident white light, say suppose it was sunlight which was falling onto this slit and Fraunhofer diffraction was taking place. Then what is going to happen is at the central maxima it will be white color. So here you will get white color, and the rest of the maxima, rest of the brightness will always be different colors. It will be a mix of the different colors. So white light is obviously, we know that it's made up of VIBGYO. So only the central point will be white and the rest all will be colored. Now one more point we noticed is if we have a larger slit width, then the sine theta will be very small, or the angle of diffraction will be very small, like exactly like how we saw it in this case over here. The angle theta is very small. And suppose the slit is very narrow, that means the slit width is very less, then the angle of diffraction will be more. But we already noticed that if slit width is less, then the width of the central maxima increases and even the intensity decreases. Angle of diffraction increase, so obviously the intensity of the resultant also decreases. So that's all about the Fraunhofer diffraction at a single slit.